Okay, we're almost to the end of module 2, and this Friday we will get the second exam. We try to format this course so that it's divided into modules. For the online tutor. In the future, if somebody wants to take this course, module 1, module 2, or module 3, depending on the background. Let me make a roll call. Awajan. Balik bersama. Kanita. Balik pro. You can do very profit. This is the one thing. This is two. That is being challenged. You can read. Pen. Food, length, so let's get started then. If there are no questions, we will start this lecture with quality factors. Quality factors are important concepts, and I think it's easier to teach this concept using circuit theory first, so that you have heard about quality factor in circuit theory. So we'll use a very simple illustration as to what this concept is. And this concept can also be used for other kinds of geometry, like the cavity, waveguides, and so on. Any resonance structure would have this behavior. That is, if you have an oscillator, the oscillator would diminish its energy as a function of time. And after a certain, the energy in the cavity would diminish to 1/e of its original value. And that is somewhat related to the quality factor. We'll talk more about that later on. So all resonators have this salient behavior. So if we were to plot the response of the system as a function of frequency, the response is usually something looking like this. That is, if you were to look at the current or the voltage in the resonance circuit, the current is very big when the circuit is at resonance, and when the circuit is off resonance, the value of the current is not that big, as you can see on the side values over here. The quality factor is a measure of how good the resonator is. The higher the Q, the better is the resonator. So when the quality factor of the cavity is 10, it resonates very well and make the current very big at resonance. And when the quality factor is small, then the peak is not as pronounced. And there's a bandwidth associated with this plot, as you can see. It will peak at a certain value, and the width of this plot is usually somewhat related to the bandwidth. The lower the Q is, the broader the bandwidth, as you can see. The higher the Q is, the narrower the bandwidth. We'll talk about this concept more in detail later on. So if you have a cavity, such as a rectangular waveguide cavity, which is the easiest one to solve. All of you know how to solve for the solution of this thing. And you actually can find a Q of this cavity in somewhat closed form by looking for places where the energy can dissipate. And when the energy can dissipate, it will take energy from the cavity mode and make it decay, just like this picture over here. Okay. So I think the easiest way to understand the Q concept is actually to look at it from a circuit theory viewpoint. Okay, I'll have this thing over here. On the left, I have the first top figure on the left. I have an LC tank circuit, and that LC tank circuit is driven by a voltage source. Okay, and all of you as electrical engineers know that the LC tank circuit looks like a short circuit at resonance. So the current will be very, very long if you were to keep the resonance frequency of this LC tank circuit. However, if you're away from resonance, the LC tank circuit is not it's not a short circuit anymore, and the amount of current that you have flowing in this circuit is finite. Okay, so another very important thing to note is that because this is an LC tank circuit without fault, it can behave in the mode of the bottom left figure, which is that if you turn off the source, yet there is a persistent current flowing in this circuit. The persistent current flow, as you all know, as good electrical engineers, that there will be a stored energy in the inductor, and the stored energy in the inductor will be composed of magnetic field, and that stored energy can pump or transfer to the stored energy in this capacitor, and when it gets transferred to the stored energy in the capacitor, the energy storage will become electric field. So the energy can flow back and forth between stored magnetic field energy as well as stored electric field energy. Okay, so it will go back and forth, just like what you saw in the undergraduate circuit theory course. And it can go on forever in principle if there's no law. However, the more realistic situation is the case like this one in the top right-hand corner, where you have a resistor in series with this LC tank circuit, and you'll find that the impedance of the circuit doesn't go to zero anymore. That is, even if you have resonance frequency, the impedance of the circuit is not zero. So the current is never infinite anymore. Okay. However, if you were to set this problem up like the bottom right-hand corner with an initial value of currents and charges in the inductor and the capacitor, then the electric field and the magnetic energy stored would cross back and forth between the two elements, and because there's a resistor in between them, the energy gets dissipated, and the behavior of the current and the voltage will look like what you have in this picture over here. Okay, so the physics is quite clear if you revisit your undergraduate circuit theory course. Okay, you revisit those concepts, the concept is very clear. And so let's derive some mathematical formulas then. So if I were to look at this problem on one of these figures over here, I know that the current can be written as the voltage in the phasor wall plus the impedance of the circuit, which is given by this. We have two elements in series, so the impedance Z is j omega L plus 1 over j omega C. Okay, and you can write this like a transfer function that you used to see in electrical engineering, where this transfer function is just 1 over z of omega. Okay, so the peculiar thing about this transfer function is that there will occur a frequency at which this denominator is equal to 0, and that is the resonance frequency of the system. So we have seen this over and again, which is that when you hit the pole of a system, you hit resonance. We saw that in the reflection coefficient of the Fresnel reflection coefficient. We saw that in the generalized reflection coefficient. We saw that in the transmission line theory. Okay, so this is quite easy to understand. However, if you have a loss, then the Z of omega is R plus j omega L plus 1 over j omega C. And then the current then would just become B of omega over j omega L plus R plus 1 over j omega C. Okay, and then the transfer function, you can call this in electrical engineering, this is called the transfer function. It is usually the relationship between the input and output. And in this case, we can think of this as the input and this as the output from a linear system theory viewpoint. Okay, so the peculiarity about when you have a small resistor is that this denominator would never go to 0 when you have a real frequency omega. Okay, so if your thing is operating with real omega, you will never have the denominator going to 0. Okay, can you see that when you look for the roots of this denominator, omega is complex. Okay, omega resonance would be omega naught minus j alpha. Or maybe you can call this, you can see that, right? I don't have to go to the details, which means that this thing now never quite go to infinity. And what it shows is that there will be a pole on the complex plane. In the first figure, there is a pole. This is real omega. For instance, if I were to look at this in the complex plane, the first one would have poles on the rear axis. Actually, there are two of them. You can actually solve for the roots of these two poles. There are two poles like that. And the second one, the poles would move away from the rear axis. Okay, they will move up, something like this, when you have loss. Okay, I won't go through the detail, but when you have loss like this, what it means is that the time behavior of the thing is still e to the j omega t. The natural solution or the resonance solution. So if I look at this system again, okay, there's still a natural solution on the bottom right-hand corner. A natural solution or a resonance solution now is defined to be the solution to this system where there's no external excitation. So that is, if I switch the voltage to 0, is there a solution to the bottom right-hand corner? So if you're naive electrical engineering student, you will say no. Okay. However, if you're not that naive and then you know how to do complex variables, you can say, I can still look for a solution to the bottom right-hand corner if I allow my omega to be complex. And then omega is the omega that will satisfy this equation over here. Okay, it will make this go to 0. So it is possible to get a natural solution even when you have a lossy system. The difference is that omega now would be one that has a complex value. So omega might be one with the real part plus an imaginary part, for instance, something like that. Okay. So if you look at the voltage now, the voltage or the current of a natural solution usually has this behavior, the homogeneous solution of the system. So what you have then is that the voltage now would be proportional to e to the j omega RT, e to the, let me see, jj alpha t. So I should actually put a plus sign here then. Okay, so I should put a plus sign there. Then I should get a minus sign. So the voltage would be behaving according to this manner. And then the current in the time domain will also behave in this manner. It will have an oscillatory part plus a decaying sinusoid. Okay. So if you want to convert this into the real world, you will have to multiply this by, you have to take the real part. You will have to take the real part of this complex signal as well, to convert them into something that's tangible and that you can measure in the lab. So the moral of the story is that whenever you have loss in the system, the natural solution or the homogeneous solution would also have to behave in this manner. So if you have a cavity, if I have a cavity, and if I have E field inside and H field inside, and there are some losses in the cavity, and those losses can come about in a number of ways. Okay, one way that the loss can come out about is having more loss. And those are also called copper loss, because in the past they used to make a good cavity with copper. Okay. Another possibility is that you have a hole. You can dig a hole, and then the hole can radiate. And that is called the radiation loss. You can also put in a lossy material. And then you will have a fourth kind of loss called material loss. Okay. So if you have a cavity such as this one, because of the fact that you have decaying sinusoids, the electric field as a function of space and time would behave something like any given position in space and time, it will have to be a decaying sinusoid. And then the H field would also have to be a decaying sinusoid. And what I have done is just to multiply by something and take its real part. So I have a sinusoidal function that is decaying with respect to time. Okay. So the electric field and the magnetic field would have to have this behavior, but we know that the stored energy, WE, in the time domain is proportional to E squared. Okay, more precisely, it's something like half epsilon E squared. Okay, and then the magnetic field stored energy proportional half mu h squared. These are in the time domain. Okay, these are in the time domain. I don't even have to put a average around it. If I average around it, then what I have then is actually okay, I don't have to put an average around it, but if I put an average around it, what happens is that this part will time average to a constant. Okay, if you square a cosine square, you know that if you have a cosine square t, the time averages to half. Okay, so something that is sinusoidal when squared will always time average to half. So if I look at this more carefully, then the total energy, which is the time average of the electric field plus the magnetic field, would have to be something that is proportional to some constant e to the minus 2 alpha t, where alpha is this decay constant over here. So the total energy stored has to decay in this manner. So is this argument convincing enough for you? That if I have a log, there will be a small exponential decay. That small exponential decay says that the energy stored will be the square of the field, or the square of the voltage, square of the current, and it has to decay with e to the minus 2 alpha t. Because the structure of the solution has to be something of that form. Is that convincing enough? Okay, I see some noise here. But you can convince yourself by doing a lot of signal processing work, which is too lengthy for us to get into. That if you have a complex pole, those poles will make contributions like the decaying signal for the elastic decay. I'm just going to say that in a hand waving fashion. Okay. So, what is the Q of a system? The Q of the system, roughly speaking, is that if you were to look at the field, the field itself, or just the field itself, say the field itself, or maybe the voltage, maybe this just grow. Okay, that quantity will go like this, and it will become exponentially decaying. Okay, and if the stored energy is 1 over E of its original value, and we call that time constant tau. Okay, so E to the minus 2 alpha t would be 1 over E if t or equal to tau. That time constant is tau is 1 over 2 alpha. Okay. So if there's an alpha associated with this law, then the time constant tau is 1 over 2 alpha. And what is the Q? The Q is number of cycles, numbers of cycles that you have in the field before it decays to 1 over E of its original value. There is number of cycles in this time scale tau. So number of cycles in radians and Q is defined to be that number. You take the resonance frequency, of course, this would be the resonance frequency. Count the number of cycles that you have in radians, not in frequency. The number of cycles that you have before the field decays to 1 over E of its original value. Okay, so the field would decay to 1 over E of its original value in that manner. And then the Q then would be omega R, which is omega R over 2 alpha, or the resonance frequency divided by 2 alpha, where alpha is the imaginary part of the resonance frequency. Where we take the complex resonance to have the real part plus an imaginary part. Okay, you will have the real part and the imaginary part, and then if we take the real part and divide by imaginary part and divide by 2, that would be the Q of the system. That is the simplest definition of Q that I can think of. So are there any questions regarding the definition of Q? Yes, Geoffrey. Yes, wall loss, copper loss. There's 3 or 4 mechanisms that can give rise to loss in the cavity. Loss to the wall by absorption by the conductive loss, which is sometimes also called copper loss, okay, because most of these cavities were made of copper in olden days. And it can also give rise to radiation loss. If there's a hole in the cavity, the energy can leak from the cavity by radiation. Or it can be having material loss. Material loss means that if you have some lossy materials inside the cavity, those lossy materials can dissipate energy and hence cause the stored energy to decay as a function of time in this manner. Okay, so there are 4 mechanisms that you can think of in the cavity that can give rise to loss. But then you will define the Q of a cavity to be this number over here. Okay. So we can also derive a more interesting formula by using energy conservation. We say that the total energy stored has to behave in this manner. Okay. By physical argument, we say that the total energy stored, the time average of the total energy stored, we can make the whole sinusoidal part disappear because that thing with this time average to a constant. So the time average of the total energy stored will behave as a function of time in this manner. And you can argue that if I have dissipation, okay, if I have dissipation in the cavity, the time average of the dissipation must be equal to the negative rate of change of total energy stored. This is just an energy conservation argument that if the cavity is losing energy as a function of time, is what it says on the right-hand side, that loss in energy must be proportional to the power dissipated in the cavity. It can be due to wall loss, it can be due to radiation loss, it can be due to materials, no manners of losses that you can think about. So this is just the statement of energy conservation. Okay. So, but we know that WT is behaving in this manner. So the rate of change of WT must be minus 2 alpha W0 e to 2 alpha T, which is minus 2 alpha WT. And this is equal to minus PD. Energy conservation. So we have another formula for alpha. Okay, another formula for alpha, which is kind of neat. Alpha can also be written as PD over 2 WT. Okay, so this is a rather neat formula. It says that you don't have to know the resonance frequency of the cavity, but if you have a way of measuring the dissipation of the cavity, you can find alpha using this formula. And of course, if you have another way of estimating the stored energy of the cavity. And as we said before, the Q don't know what is trying to do this. I have to get out of this, right? I don't know what it wants to do. I think I have to press the escape button. The only way I know how to press the escape button is to use the key. Okay, I'll get out. Okay, my flag becomes very small. I have to figure out how to go to the bottom here. And maybe put it. Okay, keep it. That's good enough, right? What is your trick again, Brandon? Oh, okay. Okay. Wow. Wow. I have a problem here. The image is upside down on my laptop. So I can't write upside down. What? I have all these cables. Not that easy. See, it's upside down. I don't know why. Does anybody know? Oh, it becomes right side up again. Okay, computers flying peace rule. They take over our lives. We just have to call out to them. Okay. Okay, so we have another way of finding alpha. Once we know alpha, as I said before, we know the Q, because Q is omega tau, it's omega over 2 alpha. So then the Q then using this approach is given by let me see if I get this right. Yeah, I think I got this right. So we have another way of finding Q using this formula. We just have to know how to estimate the total energy stored, the power dissipation, and then we can estimate the Q of the cavity. Okay. So Q is a very important concept, especially to experimentalists, because you see this kind of behavior all the time in the laboratory, that a system is never in perfect resonance, it's always in the mode of lossy resonance. So I don't have that picture over here, but what you have then is that I should have a picture here. But let me not show you the picture, but what happens is that, as I said before, if you were to plot the Q or the voltage or something, some quantity as a function of frequency, will look something like that. Okay, where this is the resonant frequency. And the reason why it looks like that is because the pole is not precisely on the real axis. The pole is actually off the real axis. If I were to say where the location of the pole is, the pole would be somewhere around here. And I think all of you did body plots as good electrical engineers. And you plot the transfer function of the system when you have a pole, and use clever techniques to figure out what the response function should look like. For instance, in this example that I've shown you, my voltage might be related to, or this could be the current too. Okay, this could be a current, and my current is related to the voltage. by this transfer function y of omega. Okay, y of omega might have a system that looks something like this with a pole. So I can say that from a very simple viewpoint, this transfer function can be approximated with a simple pole approximation. Okay, where omega r is actually that complex number over there. And you can see that this function never quite goes to infinity now. So if you were to operate yourself on the real omega axis, you will never encounter that infinity. And hence, this transfer function is never infinite. And you can write this transfer function more explicitly if I say that this pole can be replaced by this value over here, then this is omega 0. Okay, so this pole is away from the real axis and never quite encountered by you if you were to make omega real. But in the laboratory, you always make omega real because you can only measure with real omega, unless you do construct band maximum. If you think about it, all the measurements in the laboratory that you're doing, omega has to be real. Okay, so if I look at this transfer function, then you know that this transfer function has to be peak when omega is around here. Okay, omega not is good. And then it will become diminishingly small as you move away from this peak. And I guess you all know how to do that in your body plot studies. Okay, you can, if this distance is alpha, and then you can figure out that this distance, that if you are equally far from this pole in this manner, if these two are equal, and this distance is also alpha, then I think that distance here is √2 alpha, right? But the hypotenuse of that triangle is √2 alpha. So if you were to do everything right, then you will see that this thing would peak around, say, this transfer function would peak around a over omega naught plus or minus delta. And that delta that will make it go smaller, that delta is roughly about alpha. Okay, so that you can figure out quite easily using your body plot concept that you have learned as an undergraduate. And that allows you to ascertain the bandwidth of that resonance peak very easily. Okay, the bandwidth of the resonance peak is just 2 alpha. As you can see in the previous picture, that bandwidth is just 2 alpha. It's called a half power bandwidth in electrical engineering. That is the value where the peak drops to half its original power. Okay, so you can look at this thing and say that another way of looking at another way of looking at the bandwidth is that this delta omega is 2 alpha. Okay, if I look at this thing, this is the bandwidth, the half power bandwidth is 2 alpha. Okay, if you remember your body plotting, that length over there is the half power bandwidth. So the half power bandwidth of the system is roughly 2 alpha. And hence, since Q can be written so Q, as we said before, can be written as the resonance frequency divided by 2 alpha. Okay, And hence, the Q can also be written as the resonance frequency, which I have used omega naught over here, divided by the other omega. So this is another way of estimating your Q. It's just the resonance frequency divided by the bandwidth. If the bandwidth of the system is very narrow, the Q is high. If the bandwidth of the system is not that narrow, then the Q is low. Okay, does this make sense? So this is some of the rule of thumb that you use in the lab. Okay. That when you need to go back and forth between bandwidth and Q and so on, and you just have to remember these few things. So let's do some hard work here then. We have been just philosophizing so far, but maybe we can do some hard work by calculating the Q of it cavity. And to make life simple, you just use the rectangular cavity. Okay, rectangular cavity is nice because the math is simple. The physics is also kind of simple. Okay. So, but let's look at the wall loss. And the good thing about a good engineer and a good physicist is the ability to do calculations approximately, rather than having to pull out the arsenal of mathematical tools and do your calculation. So you can do things approximately, you can even do the calculation in your head. That makes you a very good engineer or physicist. Okay, so let's try to find wall losses of a metallic cavity. Use a perturbation concept. So what is special about this perturbation concept is that you can estimate this Q very easily without mobilizing the full arsenal of your mathematical knowledge. So we can think of a cavity which is made of perfect conductor. And we know how to solve for the solution of this cavity, E and H, when sigma tends to infinity. Then the Q of this system is infinite because there's no more. Okay, you have something in there, it will ring forever. So say now if I make sigma not infinite, okay, sigma finite, then there will be wall losses. Previously, the boundary condition we have is n cross E equal to 0 on wall. Now we have n cross E not equal to 0 on wall. And how do we estimate this n cross E using the perturbation concept? The idea is that you're going to do one thing. We assume that the E and H fields are going to change very little once you go from lossless case to lossy case. That is, if you switch from a perfect electric conductor cavity wall to a lossy conductor cavity wall, assuming that the cavity will still have pretty high conductivity, then the field inside E and H are not going to change very much. Do you agree? Okay, E and H is not going to change very much if we go from a low loss case to a low loss case. Okay, what is the most important thing that will change on this cavity? Will be the change in the tangential E component. Tangential E component previously was 0, but now tangential E component is not 0. That is a tremendous change, something that goes from 0 to something. That is infinite change, right? A divided by 0 always gives you infinity. Okay. So we should focus on how E changes from 0 to something. That is the most important thing. But that E actually does not change very much, but just go from 0 to something. But the H field hardly change at all. It also changes because we change the boundary condition of this problem. Before that, it was n cross E equal to 0, and now n cross E is not equal to 0. So you change the boundary condition. So one of the things that we need to calculate the Q is to find the power dissipation. The power dissipation can be found by using this formula. If I know E cross H in this cavity, and if I know how to calculate E cross H on a cavity wall, okay, and I take E cross H in this cavity, E cross H gives me the complex pointing vector. It gives me the power flow inside the cavity. And on the cavity wall, that is what we do here, I will do this integration only on the cavity wall. That's what I mean. And in order to ascertain the energy that is going inside the cavity wall, I will have to take this function vector and dot it with n. N being the normal to the cavity wall. Okay. So n is this normal. Okay. So I'm going to use a cyclic property that we have learned many times over, that A dot B cross C, okay, is equal to C dot A cross B is equal to B dot C cross A. Okay. I'm going to rewrite this in a more suggestive fashion so that it becomes N cross E dot with H star. So something that you can try at home, but very easily you can show that the top equation there can be replaced by the one at the bottom. The bottom equation is physically same thing. If you have a perfect electric conductor wall, N cross E will be 0 on the wall. And that integral for all formats is 0. But if you have a non-perfect electric conducting wall, then N cross E is not equal to 0. So we have to just method of estimating what N cross E is. Okay. So how do we estimate N cross E? So we mobilize our knowledge again that we have learned in the past. Okay. Strange. Why do I have this slide over here? I don't understand Microsoft. Okay. So what we want to do is to estimate N cross E on wall. Then we're done, right? So how do we estimate N cross E on wall? We want to make use of the fact that whenever we have a surface, and you have a plane wave coming in like this, okay? That plane wave is going to be refracted. This is epsilon 0, for instance. And then the other medium would have a complex permittivity because it's a metallic wall. But sigma is very, very large. So the complex permittivity is a very large number. And you know that all these boundary value problems can be solved using mathematical homomorphism. That is, you just have to think about a beta that is complex in medium 2, and then you have to think about a beta that is real in medium 1 above. So the beta for the medium 2 is going to be very, very long. So any k vector, any beta vector that is associated with medium 2 at the bottom will be very large. And phase matching has to be obeyed. So when the wave comes in, because this beta vector is so long, okay, it goes off the page, then the transmitted wave has to be almost normal to the interface. Agree with me on that? Because the transmitted wave has to be almost normal. So when you are in the air conductor interface, the conductor is very high in conductivity, the wave will go in and get reflected so that it is almost normally propagating on the other side. So it is like a plane wave. It will be like a plane wave on the other side, and you can actually estimate. At this place, you can estimate n cross E is going to be H tangential times Z sub n. Okay, the tangential component of the electric field is going to be proportional to the tangential component of the magnetic field times Z sub m. Z sub m is the impedance of the medium over there. And Z sub m, if it is a plane wave, you have learned that Z sub m, okay, by using mathematical homomorphism, the Z sub m is just that number. So epsilon is now a complex number. Okay, did I get this right? Yeah, so this is going to be a very, very small number. Can you see that? So Z sub m is going to be very, very small number, which is kind of intuitive to us because you're near a conducting surface. That surface impedance must be very, very small. So if you look at the equation, despite the fact that tangential H field is not 0, the tangential E field is almost 0. Because Z sub m is going to be very, very small because of the high conductivity that we are having in region 2. Okay, so you can find an estimate for the tangential E field very easily. So what you have then is that you can estimate the tangential E field from the tangential H field. Tangential H field is not 0. Tangential E field must be related to the tangential H field by this formula. So then what we have then is that even though we have n cross E, not with H, is the power flow near the surface, this is going to be something that actually proportional to just HT squared. Omega mu over 2 sigma. If you plug in all the values for Z sub n properly, the higher the conductivity, the smaller this value is. So finally, you'll find that the power dissipation is going to be half the real part of the surface integral. The tangential E field, which is going to be very small, okay, reflected by this formula, dotting with the other tangential H field. So this is essentially tangential E field dotting with that thing. And you know how to calculate this integral now, because HT is going to be the HT of the unperturbed cavity. It is not going to change very much from its original value before you put in log. Okay. So then you can actually rework this formula. You will find that it can be written as I do have to put in something. The impedance is there, though. There's a J somewhere that I have to put in. there's a J somewhere that I have to put in because it's complex impedance. So if you take this into account, then this thing becomes omega mu over 2 sigma S HT squared dS. Okay. And then of course you can estimate the total energy stored to be either using the magnetic field energy stored before you put in loss, and that value is going to be equal to the electric energy stored. So you know how to estimate the electric field energy stored and the magnetic field energy stored. They're equal to each other for lossless strategy. And that is not going to change very much. It is not going to change very much. So you know the power dissipation given by the formula above. You know the energy stored. Okay. So then you can actually calculate the Q using the formula that we have derived before, which is omega WT over CD. And then you will find that it is equal to 2 omega mu sigma. Energy stored in the magnetic field over the power dissipated on the surface, which can be written in this manner. Okay. So are there any questions on how to find the Q of the cavity with metal loss? You just go to this calculation and you can find any questions.
Can you show me the formula for Vn again?
Vn? Okay, good. Here, Vm is given by this. Remember when we have a plane wave, the tangential E, the E field and H field, if you have a plane wave, and this is the beta vector, this is E and this is H, or maybe it's the other way around. It's the other way around. Let me see, it doesn't erase now. I don't know why it doesn't erase. I don't know how this right hand rule is wrong. Okay, maybe I just put the minus sign, or maybe okay. So you know when we have a plane wave like this, we went through that in lecture 4 or something at the beginning of the course. So we find that E over H. We found that E over H is eta, which is mu over epsilon. We found that, right? For a plane wave in a homogeneous lossless medium. So I'm saying that a plane wave in the lossy medium, by mathematical formalism and by phasor technique, that impedance is also given by mu over epsilon squared.
Is it directly proportional to the fraction?
Proportional?
Well, I can also ask that question another way. So in this example, you drew the fraction very close to the normal. Does that equate to a very high Cn or very low Cn?
In this case, it's high conductivity, making beta the large number. The beta is a complex number now. The beta is going to be a complex number in medium 2.
Yeah, I know if it's closer to normal, they have to large and the factor.
The beta will be a large vector, but it's a complex vector.
That makes sense to me, but like I'm asking, I think a more simple question, which I'm just trying to see, since my undergraduate degree is in optics, instead of using the Vn, I understand it better in terms of the refractive index. And I'm asking for the, I think that refractive index is related to Vn either proportionally or inversely proportionally. And I don't know which one it is. So in this one, the answer if you tell me why like the refracted ray here goes very close to normal? Is that because the n is very high or very low?
The n actually is very small, but it's the epsilon that goes very high. I don't know why my slide jumps that condition. Yeah, again this strange mode. The only way I know how to get out of it is to press escape. Okay, into this mode. I don't know why these things are so small on this side. Does anybody know why it becomes so small? Okay, into this mode where the left hand slides are very, very small, and I don't know why. But let me answer your question. Beta is going to be a complex number, a very large complex number. Phase matching will still hold true in this interface. The horizontal component of that complex vector beta has to be equal to the horizontal component of this other beta in air. Okay, and if you just think about this, this is a very long complex vector. It just needs a very small angle here to provide a component for phase matching. You can think of this refractive index as being very high, but a complex number. In fact, we never talk about complex refractive index because you hardly have them. Okay. But in microwave engineering, you can have a complex permittivity. And electromagnetic engineering, you can have a complex permittivity. So in order to think refractive index indices a ratio of epsilon or the speed of light. Okay, assuming that you only have speed of light. But in ordinary electromagnetic, you have complex waves and complex propagation velocity. So it's not that simple anymore for the general case. Okay. So, but can you understand this physics? So I think that in the beta value of the second unit is very high, so we have to bend downward. But we only need a small component of the horizontal beta fluctuation. This matching is very important. Otherwise, numbers can be considered to be quite good. So the way that they come and refract like that, and then the refract like that is normally propagating in the second unit. And you can make the exchange of the propagation. You do study the case of it, same way and velocity in the beginning of the course. We found that it's very similar structure. Actually, say epsilon with the complex. Okay, we go back and revise that part of the course, maybe this becomes problem. Okay. I don't know why this becomes very small. Okay. Everything here becomes very small. What did it touch that makes it become very small? I don't understand it. I put my mouse over my cursor over in Control C. You see, I only know how to do this in a stupid way, which is to exit PowerPoint and try to come back again. Oh, good, wonderful. Yeah, wonderful. So let me try to finish this lecture by saying that you can now apply this formula that we have derived to a rectangular cavity. And then that is all hard work. Okay, you just have to know how to do those integrals that we have. In other words, you just apply this to rectangular cavity, find tangential H on the cavity wall, and you find this H still inside the cavity is computed, then you would have the Q of the cavity. One thing to notice is that the Q of the cavity things are all messed up. I don't know why I'm keep fixing it. It's not in. So the Q of the cavity is in a sense proportional to the volume over the surface times the skin. Because you can show that this formula, you can plug in the skin depth formula in here. This is the inverse of the skin depth. This is the volumetric integral. This is the surface integral. So roughly speaking, you can say that things are messed up again. I don't know why. Okay, I just wrote this thing for you just now, but all these pictures come around. I don't know why they're here. Okay, this puzzles me. There must be flip somewhere in Microsoft. But anyhow, I didn't want this guy to be here, but they're here. I only want this guy to be here. Okay, but Microsoft will then enter the screen for me. Okay, so that's the problem when you have monopoly. You only have one company now providing software for this kind of thing. Wonderful, this is appears. I don't know the reason. So what is the reason? Okay, you're a magician then. Okay, so you can have Q. You can have now you can actually have resonators. The Q is on the order of millions. Very lossless cavity using glass or silicon. That is Q on the order of 10. Those Qs are very good because you can use them to make filters and all kinds of things. Okay. So there's an example of how to calculate the Q of the cavity. I'm not going to go through that example, but maybe tell you something more profound. Perhaps. Hope it comes back again. Okay, it disappeared. So why is that guy in the memory sitting? Yeah, so I don't understand this. So I'm going to talk about more orthogonality. And how this is associated with the matrix eigenvalue problem. We solve for waveguide mode. We solve for waveguide mode in the manner like we say that we can reduce everything to the reduced wave equation. So if you have a scalar potential in the waveguide, it can be reduced to solving this equation. And you can think of this as the matrix eigenvalue problem if you rewrite it in this manner. Okay, so I can rewrite this equation in this manner. And I'm claiming that this problem is actually homomorphic to the matrix eigenvalue problem. So if I have a matrix eigenvalue problem, I will have something like that.
I suppose all of you had a course in matrix algebra. So we solve that problem with boundary conditions, either of the Dirichlet type or the Neumann type, and you can get all the modes of the ratio. So that problem is actually homomorphic mathematically to the next eigenvalue problem. In the bottom, we got the bottom equation. We find the eigenvalues. And in order to see the homomorphism, you can see that this operator maps to A, this function maps to X, and this eigenvalue maps to eta. Can you see that? Okay. So differential operators are actually matching operators. The next function from one state to another state, where once you apply matrix operators, next vector from one state to another state. The bottom half is taught in a lot of courses, undergraduate courses as well. And it's different to that if you have the bottom problem, if A is a Hermitian matrix, what do you know about eigenvectors as a matrix theory? If A is Hermitian, have you all had courses in the matrix algebra? You know that eigenvectors of the matrix A are coordinate with the matrix A. You remember this, like, too far back, you just to the mindset. You have to allocate it. If the matrix A is Hermitian, what eigenvector? Hermitian matrices means that A is A conjugate transpose. And A conjugate transpose means we take the matrix A, take its transpose, and take a conjugation. You know what conjugation is. And then in linear algebra, actually it's quite easy to write this. Since you have matrix elements, you just do this. This is linear algebra. Long ago, but probably like so this two problems are next to each other. And by this reasoning, all the eigenfunctions that we have in the right side actually are found each other. If you can switch it to our process operation. And it's written up on the rest of it. I think it's time to talk about it. So we are making operation very beautiful mathematical operation. Whatever you name in algebra, we apply here as well, as long as you remember this one. All eigenvectors or eigenfunctions of the right side nodes are orthogonal to each other. And these are also vectors. Those are called functions. Why is the function that I expect? Because when you do this kind of analysis, you solve functional spaces to the effective space. In functional spaces, all functions are vectors. The thing of each function can be vector. The linear algebra vector is the following. So there's one to one map. In vectors of functional spaces, you can what is the mode of orthogonality? I'll let you go because I have used up my time. Okay, and if you have good ideas on how to get Microsoft to work better, let me know. Pick up. Yeah. Yeah.
Okay, thank you. Thanks for coming.